All right, so this is the lesson for the last part of the unit, the last lesson on factoring, and in which you can tell by the title, we're factoring special polynomials, kind of special cases of factoring. Compared to the work in the last lesson, this is generally faster. I won't say it's easier necessarily, but there's less steps. And so let's get into it. So one example of these special polynomials is what we call a difference of squares. A difference of squares is when you have two perfect squares. And that's what I see here. A squared is a perfect square, same as a times a. B squared is a perfect square, same as b times b. And I'm finding the difference of them. Difference means subtraction. So quite appropriately called a difference of squares. Anytime you have a difference of squares, or again, a and b can be anything as long as they're both perfect squares, this is always the same as the factors of a minus b and a plus b. Not a squared minus b squared and a squared plus b squared. A minus b and a plus b. And so again, the best way of looking at this is to just look at some examples. But again, once you notice something is a difference of squares, we can factor it really quickly. And the two factors are almost the same. They're not exactly the same. They're almost the same. Actually, maybe before I mention it, I will say until now, we have seen this before, just the other way around. I would give you something like this, and you would FOIL it out and get that. For example, notice if I FOIL this out, a times a is a squared. A times b is positive ab. But the very next step is minus b times a, which is minus ab. Those two cancel each other out. And then minus b times positive b, which is minus b squared. Notice what I have here is the same thing I have there. Right? And we've seen this before going this way. We just haven't seen it before in terms of finding its factors, kind of going backwards. All right, so with that said, let's look at 9x squared minus 16. Both 9x squared and 16 are perfect squares. And that's because 3x times 3x is 9x squared, and 4 times 4 is 16. Hence, they're both perfect squares, which means the factors are going to be almost the same thing. They're both going to have a 3x at the beginning. They're both going to have a 4 at the end, except one's going to be plus and one's going to be minus. The order does matter. If you're, in this case, the 16 was a second term in the difference of squares, so 4 must be the second term in each of the factors. And it matters because of this part here. When you're subtracting, the order you subtract matters. So it does matter what order these terms are in. Let's look at this one. 25 and 4x squared are both perfect squares because 5 times 5 is 25, and 2x times 2x is 2x squared. And I'm finding the difference between them. And so I know that one of my factors will be 5 minus 2x, and one will be 5 plus 2x. And again, the order you write your terms matters. The order I write my factors doesn't. It doesn't matter if the first one is plus or the second one is plus. But again, because my 25 was the first term in the difference of squares, 5, which is the square root of 25, has to be the first term in each of the factors. All right, 2 more examples. Getting a little bit messier, but again, take note, these are both still perfect squares. 4x times 4x is 6x squared. 3y times 3y is 9y squared. So once I notice that, I can go right to my factors. So notice, once I notice these are difference of squares, notice how fast it is. Again, I'm not going to say that's easy, but compared to the last lesson, I think it's easy compared to the last lesson, but it's definitely fast. However, if you don't notice any of these particular polynomials or differences, or an example of a difference of squares, then we tend to just get stuck. So it's key to notice. This is why we started this unit with looking at perfect squares. We want to be able to recognize, well, first know what a perfect square is and be able to recognize them. And lastly, these are also perfect squares. And that's because x squared times x squared is x to the power 4. And y squared times y squared is y to the power 4. Again, anything that has two factors that are the same is a perfect square. They don't have to be, as long as they're the same. And so in this case, my two factors will be x squared minus y squared and x squared plus y squared. That's it. I'm not done. I factored it, but there's actually another perfect square in here. That right there that I've highlighted in green is another example of a difference of squares. And again, that's almost in the exact same form I gave you at the beginning here. Instead of a and b, I have x and y. And so just that part that's highlighted in green, I can break down into 2 more factors. So what's highlighted in green is the same as x minus y and x plus y. However, the other factor, x squared plus y squared, there's nothing more I can do. A common mistake is to think that this part right here is the same as x, I'll make my marker a little less thick here. There we go. Common mistake for what I've highlighted, sorry, underlined in red, is to think that that's the same as like x plus y times x plus y. But that's wrong. Again, if we multiply x plus y times x plus y, we'll get 3 terms actually after we collect like terms, not 2. Which leads us actually to the last part, which is not a difference of square, but a perfect square, factoring a perfect square trinomial. Okay, this is a little bit trickier, and so the examples will definitely help. But if something is a perfect square trinomial, which means it's 3 terms, but it's a perfect square, which means its 2 factors are exactly the same, which we actually saw, if you recall, in the very last question from last day's final problem. It had to do with the area of a circle. And one of the factors we knew had to be a perfect square. That said, if something is a perfect square, it should always be in this form. First, it always has a first term that's a perfect square, and a final term that's also a perfect square. However, there's always a middle term. And the middle term can be positive or minus. That's why there's a plus or minus here. It can be a positive term or a negative term. And the middle term is always 2 times the square root of the first term times the square root of the last term. I expect that seems a bit daunting. So let me just write out what the factors would look like, and then, like I said, use it. So if I have something that is a perfect square, the 2 factors are going to be exactly the same. In this case, it'll be a for one of the terms, b for the other terms. But they're either both going to be plus or they're both going to be minus. Whatever goes here, whether it's plus or minus, it has to be the same. It's going to be the same as whatever symbol you see there. And again, if I have the same factor twice, we usually would write it something like this. A plus or minus, depends what's in there, all squared. At this point, this is getting too abstract for me to go on any further without giving some concrete examples. But again, if something is a perfect square trinomial, if we have 3 terms that really is a perfect square, that means the 2 factors must be identical, perfectly the same. So these 2 examples you see here are both perfect squares. How do I know that? Because x squared is a perfect square, and 9 is a perfect square. That's the easiest part. The hardest part is realizing, like, how do I know that is part of a perfect square? Because 6 is not a perfect square. But again, the middle term should always be the same as the square root of that, which is x, times the square root of that, which is 3, times 2. And x times 3 times 2 is 6x. And that's what it says right here. This middle term is always 2 times the square root of the first term times the square root of the second. All right? Of the last, I mean. Either way, even if that's challenging, which I completely expect, more importantly, I'm telling you this is a perfect square, which means I can jump straight to the factors. I know the factors are going to be exactly the same. I'll just write it like this. Actually, no, the first time I'll write both out, copies of them. And I know the 2 factors have to have an x and a 3 and an x and a 3. I know that. Again, if you're still not sure how I can tell this is a perfect square by looking at it, fair enough. But for the time being, just trust me, it is. And therefore, I know the 2 factors have to be the same. And so there has to be x and a 3 and x and a 3. Whatever goes here, whether it's plus or minus, has to be the same. And it's always the same as what we see there. So if I'm adding there, I'm adding here. And notice, if I multiply this out, for that middle term, the first thing I do is x times x, which is x squared, x times 3, which is 3x, and then right here, x times 3, which is another 3x. Notice, that middle term is the same as the x times 3 twice. That's what that is. That middle term is always the same as the square root of this times the square root of this times 2. In this case, 3x times 3x. 3x plus 3x. That's it. There's no way around it. The hardest part, I think, will definitely be how to recognize if something is a perfect square or not, which is the final problem. So with that said, though, if I have the same factor twice, why not just write it as x plus 3 squared? Okay, so keep in mind, especially if we just know that this is a perfect square, or you're told it's a perfect square, we should be able to go from here to here in like a few seconds. We just have to think what times itself equals x, what times itself equals 9, and pay attention to whether you're adding that middle term or subtracting. That's all we have to pay attention to. So this one, almost the same thing. It's a perfect square because x squared is a perfect square and 9 is a perfect square. The middle term, again, I'll get to that in a bit, but I just right now, just trust me, it's a perfect square. And so I know the 2 factors must be x and 3. I know it must be minus here because there's a minus there. And it's the same factor twice, so I'm done. Now that's it. It's not wrong. to look at this and think of two numbers that multiply to 9 and add to -6, you'll get -3 and -3. It's not wrong at all. But also, if we recognize this to be a perfect square, what I'm doing is really quite quick. And again, notice that middle term, minus 6x, is the same as x times -3 times 2. And again, the reason that works is because if I was to FOIL this out, at some point I would go x times -3 twice. That's why. And again, that x and that -3, or the x and the 3, I should say, are both the square roots. You know, x is a square root of x squared, 3 is a square root of 9. Again, it's one of these things that in practice gets easier. The more to just explain it in words is always going to sound a bit confusing. So here's two more examples that are, again, very similar. So first, how can I tell this is a perfect square? Well, let's look at the first term. 4x squared, that's the same as 2x times 2x. So I'm going to start with that. That means if this is a perfect square, inside my factors, that's going to be a 2x, because 2x times 2x is 4x squared. Over here, I have a 9. That's a perfect square, which means if this is a perfect square, my factor is each going to end with a 3, because 3 times 3 is 9. Now what about the middle term? Well, no, let's check. The middle term has I'm subtracting. So if this is a perfect square, this is going to be subtraction here. And so let's see if this really is the same factor twice. Because honestly, now to figure out that middle term to see if this really is a perfect square, you know, all I have to do is look at this times this, and 2x times -3 is -6x, times that by 2, and I do indeed get -12x. So I know with certainty that I'm correct. I know that this is a perfect square. And I was able to factor this quite quickly, even though there was a coefficient of 4 in the front that I couldn't factor out. And again, it all hinged on knowing that this was a perfect square. And I showed you how I could kind of check in case I wasn't sure. And so again, right here, I know this is a perfect square. And I know it's a perfect square because I made the question, and I can check in a second. But again, once you know it's a perfect square, it's as quick as this. What times itself equals 4x squared? 2x. What times itself equals 9? 3. What sign is right here? A plus. So 2 of those factors, and I'm done. That's it again. And this leads me into the final problem. How can I confirm that this is a perfect square? Because right now I just told you it is. Just check. Go 2x times 3, which is 6x. Take that and times by 2, which is positive 12x. And yeah, that's the same thing I have in my middle term. So I'm hoping by now that this idea of that middle term of a perfect square is not easy to figure out, but I'm hoping it's getting easier because we looked at a few examples. And like I said, especially if we just know, if I just tell you this is a perfect square, you don't even have to check. It's just, like I said right here, how quickly I wrote that down. But the final problem now is looking at, you know, how to tell if something is a perfect square or not. All right, so I have here 9 different polynomials. And as it says up here, I only want to factor the polynomials that are perfect squares. If they're not, I'm just not going to do anything with it. So all this is about determining if these are perfect squares or not. Probably the hardest part of this lesson. I highly, highly recommend that you pause the video here and actually try this on your own. At this point, just hearing me talk and watch me do things, I don't think it'll be nearly as beneficial as you trying it first, making mistakes potentially, and then checking it over. So I'm going to pause for a moment. I really encourage you to pause this video. Hope you pause the video. Anyways, I'll look at these one at a time. So again, here, this is all about checking if it is a perfect square. If it is, I'm going to factor it. If not, I'm going to do nothing. So is this a perfect square? Let's see. A squared is a perfect square, so that's a good sign. 16 is a perfect square, so that's a good sign. But I have a negative there, and so I know this cannot be a perfect square. If I go back to up here, if you look at all these examples, if you look right here and here and here and here, or even just right there, that last term has to always be positive. And that's because if it is a perfect square, at some point you're going to have one term times itself, and any number times itself is going to be positive. And so as soon as I see the first term or the last term is negative, I know it's not a perfect square. Nothing more to do. Let's look at this one. This might be a perfect square. The first term is the same as 2b times 2b. The last term is the same as 1 times 1. All right, so now I'm going to do a bit more. I still don't know for sure if it's a perfect square. If it is, though, my first part of my factor would be 2b. The last part would be 1. And there I'm subtracting the middle term. So if it is a perfect square, I'd be subtracting here. But is that middle term correct? Let's see. The middle term should be 2b times negative 1, which is negative 2b, times 2, which is negative 4b. So I'm correct. So I know that not only is this a perfect square, I know that its two factors. Not easy, but fairly quick. I didn't have to break up the middle term and do any of those things. Although, again, if you would ever think of multiplying these together and finding two numbers that multiply to 4 and add to negative 1 and do all the work from last day, that is fine. It's just not nearly as quick as this. OK, next. Is this a perfect square? Nope. It only has two terms. Okay, then to be a perfect square trinomial, it has to have a middle term. A common mistake is to think this is equivalent to c plus 8 all squared. But that is a common mistake, right? We can't just distribute these. I got too much stuff going on. These aren't factors, the c plus 8. They're different terms. And that goes back to the beginning of our unit on polynomials. So nothing more to do there. Let's look at this one. Is this a perfect square? Well, it has three terms. That's a good sign. The first term is 16, which is the same as 4 times 4. The last term is 16d squared, which is the same as 4d times 4d. So I'm going to keep going. This may be a perfect square. If it is, the first term in the factors is going to be 4. The second term in the factor is going to be 4d. As well, my middle term, I'm adding it. So if this is a perfect square, I'm going to be adding this. So again, if what I gave you is a perfect square, then I've factored it. But let's check, because it's all about that middle term. The middle term, in this case, should be 4 times 4d, which is 16d, times 2, which is 32d. Yep, it's a perfect square. We're good. Let's look at this one. 1 is a perfect square. 64e squared is a perfect square. So it looks encouraging. So if this is going to be a perfect square, it's going to be 1 and 8e right here. And I'm going to be subtracting the 2. And let's confirm if the middle term of what I gave you really is correct. And the middle term of what I gave you should be 1 times negative 8e, which is negative 8e, times 2, which is negative 16e. We're good. So we're correct. This is a perfect square. Let's look at this one. Is this a perfect square? Well, f squared is. F times f is f squared. 6 is not. 3 plus 3 is 6, but not 3 times 3. So this is not a perfect square. Nothing more to do. Is this a perfect square? Yep. G times g is g squared. 10 times 10 is 100. So the middle term I'll get to in a bit. But if this is a perfect square, my factors are going to start with g plus 10 both squared. And I did that pretty quickly because I've been kind of saying the same things over and over again now. That's it. Let me just double check. G times 10 is 10g, times 2 is 20g. Yep, we're great. And so let's look at the second last one. Getting pretty messy looking, but 49h squared is the same as 7h times 7h, and 1 is the same as 1 times 1. So let's see. Let's prepare ourselves to assume this is a perfect square, but then always check. And so in my factors, I'm going to have 7h and 1 here. I'm subtracting my middle term, so I'm going to be subtracting here. And let's just check. 7h times negative 1 is negative 7h, times 2 is negative 14h. And so we're good. Which leads us to the last one. Is this a perfect square? Well, it looks promising. I times I is I squared. 3 times 3 is 9. So let's go with it. I'm going to have I and 3 here. I'm adding my middle term, so I should be adding these. And so if this is a perfect square, these will be my factors, but let's check if that middle term is correct in what I gave you. Here, if it is correct, it should be I times 3, which is 3I. I will literally be done in like 10 seconds. Yeah. Oh, like literally 10 seconds. And so I times 3 is 3I, times 2 is 6i. Well, I have a 9i here. So that means these are not the factors because this was not a perfect square. And just like that, I'm done. OK, pretty abstract. Can be pretty quick. It's the last lesson, so that shouldn't be surprising that's the case. I'm going to stop talking now.